In this lecture, we'll be looking at numerical integration techniques to carry out multidimensional integration. So, the numerical integration techniques that we have considered so far are basically done in one dimension. So, the Newton Cotes method, the Gauss quadrature, even the Richardson's extrapolation and Romberg integration, those are carried out for a single integral or integral in one dimension. However, in many engineering applications, integration are usually carried out across two dimensions or even higher. So an example is to calculate the flux, which is actually the surface integral of your vector field dot product with your unit normal vector. So in this lecture, we'll be focusing on techniques that we can use to evaluate multidimensional integral numerically. So the first method that we're going to look at is known as the Monte Carlo method. So to illustrate the concept behind the Monte Carlo method, let's say you're asked to do this integral where you have I is equals to double integral of f of x and y dA. So what is R? R is your domain of integration, and the function f is the function that you want to integrate. So with the Monte Carlo method, what we want to do initially is we want to generate a series of randomly distributed points across x and y. Since we are dealing with a double integral, we will be having random points that are distributed across x and y. So these points can fall outside your domain of integration R, or they can fall inside your domain of integration R. So here I'm just using different colors to separate the points that are inside and outside of your domain. So with step 1, we generate a series of randomly distributed points, which can be either inside the domain of integration or outside the domain of integration. So if you have 100 points, you're going to run a for loop to determine whether each of these points is inside or outside the integration domain. Once you have run the for loop to determine if they're inside or outside, you can actually estimate the area of your domain of integration by calculating the percentage of points inside the integration domain. So let's say in this case you have distributed 100 points and 50% of the points fall within the integration domain. So the area can be approximated by the percentage of points that are inside your integration domain. Now, that only gives you an estimate of the area. In order for us to find the value of this numerical integration, what we have to do is we have to run a summation from I equals to 1 to n of f of xi yi. Okay, and what we are going to do next is we're going to multiply this summation with the area that we estimate based on the percentage of points that is within the integration domain, and we divide it by n. So this is the Monte Carlo expression for a double integral. So in this case, n represents the total number of points that we have distributed randomly across the xy plane. A is the area that we have estimate based on the number of points that fall within the integration domain, and f at xi yi are basically just the value of f evaluated at each point I, which are the points that you have randomly distributed. So the Monte Carlo method, the concept behind doing the two-dimensional integral is very straightforward, and you can extend it to 3 dimensions by distributing randomly distributed points across the 3-dimensional space. But there are limitations to the Monte Carlo method. For example, any algorithm that we use to distribute or generate a randomly distributed point is actually not really random. Sometimes when they do a random distribution, we'll find that there will be a cluster of points in one side and less points around the other side. So if you have something like this and you have a domain of integration this way, you can see that the cluster of points around here will make the approximation of your integral less accurate. That is one thing. The other thing is, in order for you to get more accurate solutions, you might need to have a lot of points. So if the number of points is significantly large, this can be problematic when it comes to performing your numerical integration, because it might take a longer time. So this is the Monte Carlo method, which is based on randomly distributed points. Another way of doing our multidimensional integral is based on gridded data. Okay, so an example that I can give you is, suppose that you're asked to do a multidimensional integral, in this case a double integral of x squared y dx dy, and the limits of integral are given by 1 to 3 and minus 1 to 2. if you want to solve this integral analytically, what we will normally do is we will integrate in the x direction by treating y as a constant, and then substitute the limits before we actually do the integral in the y direction. So this eventually will give you a single value. The concept behind numerical integration for multidimensional integration is the same. You're going to carry out your integral in one direction first, use those values to do numerical integration in the second direction. So if I'm going to represent this as a flowchart, you can think of it this way. So you start your algorithm, you are going to solve the inner integral first. Once you have solved the inner integral, you're going to use all those results. When I say solve, I mean you solve it numerically. So once you've solved an inner integral numerically, you are going to solve the outer integral by using all the values or solutions that you have gotten from the inner integral, and then the results that you get would be the estimation of your double integral. So this is the flowchart if you have a double integral. If you have a triple integral or a multi-dimensional integral, basically the flow is roughly the same. You solve the inner integral first before you solve the outer integral. But because you have more than two integrals, you are going to run an if statement to determine whether there are any more inner integrals to do. So you're going to progress or proceed with this step by step. You do the inner integral followed by the second inner integral and so on until all the integrals have been covered. So that is a flowchart that we would have to use if you're going to solve multidimensional integral using grid-based approach. Okay, so what is the concept behind solving a multidimensional integral? Let's say you are asked to determine the volume under this surface. From your maths unit, you have already known that if I do a double integral of a function of x and y dA over your domain R, this represents the volume under the surface f of xy. Very much like how a single integral is actually the area under your curve f of x. So if you're asked to find the volume under this surface fx, f of xy, so this is a surface f. In order for us to find the integral, what we want to do initially is we want to discretize our volume into thin tiny strips. Okay, so we are going to cut our domain into thin tiny strips such that we have something like this. Okay, so we're going to cut it into thin tiny strips, which can be represented as this form here. Now once you have discretized your volume into thin tiny strips, what you are going to do next is you are going to determine the volume under each strip, and once you have the volume under each strip, you are going to sum all this volume up, and this would represent the volume under the entire surface. So that is the concept behind doing multidimensional integral. You're going to do the integral in the x direction followed by y, but effectively what you're doing is you're doing a discretization of your surface into tiny strips like this, and for each strip you find out what is the volume underneath it, and then you do the same thing for the second strip, find out the volume underneath it, and you're going to proceed on until you cover all the strips. Once you have done that, you are going to sum up those volumes to get an estimate of your double integral. So I'm going to show you an example in the next part of this lecture to see how the multidimensional integral can be carried out. Alright, let's say you are asked to do this double integral where the function that you're supposed to integrate is given by x squared plus y squared. So x squared plus y squared can be represented by this surface here, and this would be your x squared plus y squared. So the limits of integral in both x and y are from -1 to 1. If you do this integral analytically, you'll find that the solution is 8/3. Now what if you want to solve this numerically? And just for the sake of illustration, let's say we are going to use the composite trapezoidal rule. So the first step in what you're supposed to do with this multidimensional integral is to discretize the x and y direction. Okay, so you know your limits of integral are from -1 to 1 in both x and y. So in the x direction, you're going to discretize it into small number of segments. So in the x direction, you can discretize it where each segment known as delta x is basically your b minus a over n. Or in other words, you have 1 minus -1 over n. N would be the number of segments that you want in the x direction. Okay, and then you're going to do the same thing in the y direction. You're going to discretize it such that the width of each segment would be given by d minus c over n. In this case, this would be your c and this would be your d. So you have something similar. You have 1 minus negative 1 over n. Now the n that you use, or the number of segments that you use in the x and y direction, they can be different. Alright, that it is not necessary for you to use the same number of segments for both x and y. So this is the first step that you're going to do. You're going to discretize both x and y directions such that you find the width of each segment. What you are going to do next is you are going to start integrating in the x direction, because in our integral here, the inner integral is with respect to x. So what we're going to do is we're going to integrate in the x direction first using the composite trapezoidal rule. Okay, so how do we do it? We are going to do this composite trapezoidal rule for every value of y. So what does it mean by every value of y? If you recall from before, in our first step, we have discretized the x and y direction into n number of segments. So what happens then is you have different values of y corresponding to the different segments that you have. So for example, the first value of y is given by y0. This would have been y1, y2, y3, and so on. Okay, so you're going to carry out your composite trapezoidal rule for each value of y. So let's say we start off by saying that y is equals to y0. If y is equals to y0, we are going to calculate the numerical integration in the x direction using composite trapezoidal rule. So let's say the value of the integral that you do in the x direction is given by I0. Okay, so using the formula for the composite trapezoidal rule, you are going to get delta x over 2 times f at x0 y0 plus 2 times the summation from 2 to from 1 to n minus 1 of x I y0, because we are doing it only for y equals to y0, plus f at the last point xn, again y0, because y0 value of y is fixed at y0. So if you're confused or not sure where I got this from, this is actually your composite trapezoidal rule formula. If you don't remember, please refer back to lecture 7. Okay, so at y equals to y0, you can calculate the integral in the x direction, which you obtain I0. What we're going to do next is we're going to repeat this same thing for the next value of y. So in this case, we are going to do it for y equals to y1. So for y equals to y1, you're going to get I1 is equals to, again, delta x over 2 f at x0 instead of y0, because y is y1, we get y1, plus 2 times the summation of f at xi y1. So here you have n minus 1 I1 plus f at xn y1. Okay, so this will give you the second value of the integral in at y equals to y1. You're going to do the same thing for the remaining values of y. So eventually what you have is you have different values of y. You have y0, y1, y2, and so on, and then you have the corresponding values of the integral that you get, which is your I0, I1, I2, and so on. So having this list of tables, or having completed the integral in the x direction for all values of y, what you want to do next is you want to do the integral in the y direction. Okay, so when you do integral in the y direction, this will be the table of values that you are going to use. Okay, so let me write it here again. From your first step, you get all these values of what I corresponding to different values of y. Okay, so in order for you to estimate the double integral, what you want to do is you want to integrate in the y direction. So this table here, you can assume that you have your y and have your I. So each of these will correspond to different values of I against y. So when you do an integral in the y direction, the value of your integral, which is the volume, will be given by, again, using composite trapezoidal rule, you're going to integrate in the y direction. Because it's in the y direction, you will get delta y instead of delta x. Okay, so you have delta y of I0 plus 2 times the summation from 1 to n minus 1. This will be your I at any value I plus in. Okay, so if you look at what we are doing here, where we do the integration in the x direction followed by the y direction, you can see that the concept here is very similar to your multidimensional interpolation. where you actually interpolate in the x direction first, gather all the values, and then use those values to do interpolation in the y direction. The same thing happens here. You do integration in the x direction first using either the trapezoidal, composite, Simpson's 1/3 or Simpson's 3/8. Once you have done that, you use all those values and do the integral in the other direction. Okay, so conceptually this is how the numerical integration for multidimensional integral works. Similar to what you do analytically, you do the integral in one direction first, followed by the other. So if you're going to program it, or if you want to develop MATLAB code for your numerical multidimensional integral, you would have something like this. So you have this trapezoidal rule function which implements your composite trapezoidal rule, but then here you have your for loop. This for loop will loop over the different values of y. Okay, so if you recall earlier, we do our integral in the x direction first, so this will loop over all the different values of y, your y0, y1, y2, and so on. Okay, so for each value of this y, you are going to solve the trapezoidal rule, or you're going to use the trapezoidal rule to solve the integral in the x direction. Once you have gathered all the summation x values, you are going to call the trapezoidal rule again, but this time you do the integral in the y direction.